Hello everyone, this is Yu-Shiang. It is my pleasure to present our work RigidFusion, RGB-D scene reconstruction with rigid removing objects. This paper is a joint work with Changjian, Matthias, and Niloy. In this paper, we address 3D reconstruction problem using RGB-D input. Amazing progress has been done in the last decade. Now, we can reliably reconstruct high-quality scene geometry, as shown in the right image. However, if you look into video carefully, you will find this is different than our daily environment. Our daily environment contains many dynamic events, like those two examples. A person is moving an object from a corner of room to another place. This is a target environment we want to reconstruct. The input will contain large object motion and camera motion. And if we directly apply the standard method in a dynamic scene, the reconstruction will fail, because static environment assumption is no longer whole, as shown in the demonstration here. This inverse problem has a complex solution space. One required to solve in background segmentation and uses segmentation to estimate camera motion. To reconstruct any foreground object, one required to detect and segment rigid object and non-rigid object. After segmentation is predicted, the correspondence need to be estimated and established across multiple frames, and all those things need to be done efficiently. Because segmentation is unknown, this problem has a cyclic dependency issue. To robustly estimate motion, you will require accurate segmentation. To predict accurate segmentation, you will require accurate motion estimation. And this becomes more difficult when we have a non-static camera, as shown in the right image. In this example, both camera and the chair are moving along the same direction. The motion difference will be small, hence a robust detection method is required. While the ground truth motion may be similar or ambiguous, the local motion estimate has another issue. If you estimate motion of a patch or a superpixel, this small segment of the pixels might be weakly constrained, so the local estimation may be wrong, as the example shown here. This is an example from previous work, which jointly solving tracking and labeling. The labeling is done using the motion residual. However, it's required to assume the local geometry has strong feature, which can constrain the tracking problem. If the local estimation is wrong, it's likely it will affect the quality of tracking and also reconstruction. As the problem is difficult, previous work using different strategies and assumptions to tackle this problem. Here is a method focused on capture background model in dynamic scene. They either using semantic segmentation or solving motion segmentation using the camera tracking arrow. And here it includes dynamic blend, static fusion, and RigidFusion. Another direction of previous work focused on handle non-rigid object. They only reconstruct single non-rigid object and ignore rigid object. This including dynamic fusion, killing fusion. Or they will also reconstruct the background, such as mist diffusion. And the third type of work focuses on reconstruct both background and the rigid moving object. It can be further categorized into two types of work. One type of work using template or semantic segmentation of the object prior. Another type of work do not use prior. Without using prior, the system will be more generalized at test time. For different kinds of input, different object types, different geometry. This is a setting we want to address in this paper. Now let's see our problem statement. We take RGB-D video as input and output full scene reconstruction. We do not use any object required or required to pre-scan the static background. To regularize the problem, we import following assumptions. We only reconstruct rigid moving object and the background. We will assume moving objects are not moving simultaneously. Here is our system pipeline. The green color represents the foreground module, and the blue color represents the background module. Let's start from the beginning. We take an input frame, and we detect human segment. As a human is a non-rigid object, we use the overshot method and run human detection frame by frame. Then we use the segmentation output to remove human segment. As shown in the right image, the segmentation boundary is not accurate, which is expected because semantic segmentation is usually not perfect. So our system still need to deal with this kind of outlier. Fortunately, we can handle this in the next step. Next, we estimate camera motion and build our background model. We estimate the camera pose, use frame to SDF tracking with geometry turn and photometric turn. And we remove segmentation outlier and the dynamic element using free space over fusion. As a demonstration here, this approach can effectively remove outlier and the dynamic element without running a segmentation network. So how does this being done? Let's see how this works. Recall that in a standard TSDF fusion, we only record muscles inside truncation region, which is marked in blue or red color here. In the previous one, the refusion, they also integrate muscle that has positive SDF value. Although this approach can also smooth out noise, it will take many frames to average out the noise. In our system, we propose to maintain its sharp background, which record frequency that the muscle being identified as free space muscle. Then we define a threshold to identify which muscle has been frequency observed. And this can allow us to aggressively and immediately remove any outlier to prevent the tracking being polluted. We show that this step can be effectively done by modifying standard volumetric fusion step. Before integrating muscle, we will check whether it is the free space muscle or not. If it is not free space muscle, then having a side distance value larger than truncation value, we will update the free space count, and we will keep track this count. Once this count is larger than a certain threshold, we will mark this muscle as free space muscle. Next, we introduce how we handle foreground. We use an asynchronous tracking scheme. Specifically, we don't track both foreground and background simultaneously. Instead, we delay foreground tracking by delta frame. This small delay allows the background model to accumulate more free space information. This is similar to supplement obturation, which uses multiple frames to achieve robust tracking. Using a proposed asynchronous scheme, now we can introduce how we detect dynamic objects. As mentioned earlier, a small delay gives us a good background model in runtime, and we can query this background model to identify a point located in a free space. Those unknown free space pixels are marked in red color. As you can see in the image, it produces a very nice initialization, but we still need to handle segmentation outlier. To start foreground tracking, we check the area of the unknown segment provided by the previous step. If the area of unknown segment is larger than threshold, we will initialize the foreground tracking. Again, we will track the foreground object using frame to SDF objective and free space aware fusion. The cumulative weight in the foreground model can be used to further remove outlier, as shown in the image. If we have a wrong foreground detection, for example, we track a noise from the background, the tracking will usually fail due to lack of correspondence. If this happens, we will deactivate the foreground tracking and remove the model. Now let's see a demo in runtime. In this example, our system robustly detects the foreground object and track and reconstruct the foreground model without import segmentation formulation. Our system also supports multiple object tracking. This can be done by employing heuristic to reset active foreground object and the background model, as shown in the pipeline. Here we import heuristic to assume two dynamic objects will not move simultaneously. So, if we detect object becomes static, we can reset the system and to detect a new object, as shown in the example here. The second so far has been successfully detect, track, and reconstruct. After the tracking is done, we import two offline processing steps to improve the quality. This includes backward tracking to recover the full trajectory if there's misdetection, and we reoptimize the background model using all foreground model. In the third step, we perform matrix to extract output mesh. Now let's see our output for the reconstruction. Our system successfully reconstructed the 4D reconstruction in this dynamic environment and built the full trajectory of these two moving objects, without assuming we know the type or the semantic label of those moving objects. Here we summarize our approach. We handle cyclic dependency by importing synchronized processing and the free space aware fusion. And we solve motion segmentation by segment by reconstruct step. We achieve multiple object tracking by reset the active object. To conduct quantitative evaluation, we create 20 synthetic scenes as a test set. The object motion is synthesized using Open Motion Planning Library. We design a metric to evaluate both reconstruction and tracking, and compare with various scene-1 methods. We show a simple example of our test set. Now we show our evaluation metric. To evaluate reconstruction, we use transfer distance to define position and recall. Here, in example 2 and example 3, both results has inaccurate reconstruction due to poor estimate of pose or the wrong segmentation. So they have a low precision. The fourth example shows a partial reconstruction, which is caused by the slow detection and the wrong segmentation. In this example, it has a low recall. To evaluate tracking, we import metric from standard visual object tracking, and we enforce one-to-one mapping because we don't want the tracker to switch target. The NOTM metric here defines the overall tracking quality. NOTP is similar to ATN RNSE to estimate the absolute error. The partial detection shown in example 1 has a low NOTA because it only detects a part of trajectory. The second example shows good detection but poor tracking, so the NOTA is still low. The third example shows a complete trajectory and also accurate estimation, so it achieves the best NOTA. Here is the evaluation result. We evaluate against different methods, and our method has the best tracking accuracy and the reconstruction. We even perform better than the method using semantic segmentation prior. The main reason is semantic segmentation does not directly give you motion segmentation. In a difficult example, there will be too many positive detection, so that another robust method will still be required. Here is the qualitative result in our synthetic test set. As shown here, conversion can only output partial reconstruction. This is caused by the slow detection, and the local estimation is not accurate, so the segmentation cannot recover the flow object. RigidFusion employs a high accuracy semantic prior, but the reconstruction output contains a lot of noise. Our method not only handles noise, also output a complete trajectory and a nice reconstruction. We also conduct qualitative evaluation using real-world data. The data is recorded using structural sensor and iPad L2. To achieve a fair comparison, we pass human detection output to other methods by a mask-out depth pixel, and we test and collect the different kinds of settings involving small thing, big thing, low dynamic, high dynamic. In the first example, we record a thing with a static camera. In this simple example, all compared method can detect the foreground object. Our method also works and able to remove segmentation outlier. As shown here, RigidFusion result contain a lot of noise due to inaccurate instrument segmentation. In the second example, this is more difficult because the camera has non-static motion. Both conversion and RigidFusion start to produce inaccurate tracking, and the reconstruction become unaligned and contain more noise than the previous example. And this is because when the camera starts to move, the detection becomes more difficult. This is also a reason why they cannot successfully detect the second object, because the background model is already polluted and contains too many outliers. The third example has higher motion ambiguity, and they contain many objects in the scene. This becomes more challenging to conversion and RigidFusion. As shown here, the conversion detects multiple foreground objects, and the RigidFusion is struggling to find the actual dynamic object. Our methods still work well and produce plausible results. The last example shows a scenario where the dynamic objects start to move in the second frame. This example requires system to quickly segment out dynamic element and maintain a robust tracking. Our method still produces good results.